Can everyone see?
Yep.
All right. So as you all know, I'm very interested in neuroscience. So I'm gonna talk about Julius, and I don't know whoever this is, but something like that. So they are the winner of the 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 prize?
Lovely.
Yeah, and they find out something called TRPV1, which is receptors in thermal sensation. So as you can see in the slide, Julius discovered receptors for temperature and pressure. And how did that impact the field of neurology? Basically, since last time the scientists don't know how these receptors, or is there any receptors for temperature or pressure. So this is very useful, and later on I'll show you why. So this experiment results provide a molecular and neural basis for this thermal sensation and mechanical sensation. Mechanical sensation is transduction, as you can see here, meaning here. So it's actually how we feel physical force, like touch, vibrations, something like that. And thermal sensation is, of course, temperature changes outside of the skin. So it's actually like if you're in a cold, if you put your hand into ice water, right, and you take it out, and you don't have to put in the hot water, you just put into normal water, you actually feel hot. That's how thermal sensation works. It's not exactly accurate. It's the changes in the environment. Okay, so the experiment about this was, so he uses something called capsaicin. It's a compound in chili pepper. So you know, right, when you put chili on your skin, you actually feel hot. So they use this to do this experiment. And then they found out that the receptor is an ion channel, is TRPV1, is actually activated when they put this thing on skin. And then they find out that, so they identified the gene that code this, and etc. And then the response was given out by our skin was provide high concentration of protons, and then a lot of chemical compounds was generated. And then they proceed on making it more reliable. So then they did not just do this, and then they also do some experiment on mutated mice. So these mice, right, they don't have actually is deficient in TRPV1. That means that they should not feel hot, or like their sense in thermal will be less accurate. So it's exactly what they expect. So less, so the deficit in heat sensitivity, and a marked reduction in inflammatory and cancer pain. So then they actually make it more reliable. And then they did another one on vampire bats, and they assume TRPV1 as infrared sensors, because infrared is considered as heat, right? Okay, so I'll go on with fun facts. Okay, oops. So do you know that actually brain surgeons can operate inside the brain without anesthesia? You know why? Because the brain doesn't feel pain. It's only the structures around the brain that feel pain. So if you somehow get into the brain, they don't feel pain. You can just do something inside and they won't feel anything. Okay. Let's talk about his partner, this guy, Pata Potian. Okay. So he discovered a family of pressure sensitive ion channels. They call it the piezos, you can see here. And then he confirmed that they're actually essential for to sense pressure. As you can see, piezos they code for pressure sensing channels. So in our body, it's actually all ion channels around it. So it acts to sense pressure with nerve terminals. It's actually a lot, but I didn't list out all of them. It's quite a lot of things going on with piezos. And then, as you can see, it will open up a door to understand biology in health and diseases. Yeah. So basically, they discovered a very, very advanced. So it's very useful nowadays, and actually more to discover in neuroscience. Unlike other science, we still don't understand many things in the brain. Okay, another fun fact. You can actually control pain. And look at the picture. This is before meditation, and this after meditation. As you can see, the frontal lobe, the parietal lobe. See. So yeah, meditate more. I think it's good for yeah. So I would like to just give you guys some vision of what neuroscientists can do. So like I said just now, I like other fields of science, like we know we can build rockets and so many things, but we can't actually do many things with brain now because we don't know much about brain. You see, they say neurons related to memories, but they actually no details evidence, and then they can't explain how exactly it works. So they say it is memory is because of neurons, but they don't understand how it works. How brain simulate future, so how you think, how you plan and everything, they don't understand how this works. So they don't know how predictions are formed. They don't know why we can form predictions. Yeah, and that's the end of my presentation. Okay, thank you guys.
Nice. Okay, here's what we'll do. We'll proceed with the rest of the presentations first, and then at the end, if you guys want to open up for discussion, then we can ask questions and stuff to each of the presentations, and we can go back to the slides and stuff later. Okay? Cool.
Okay.
So next is Zilong. Do you want to share your screen or should I share mine?
You can share your screen.
Okay. So just going past Sean's ones. All right, go ahead.
Okay, so today I'll be talking about cable bacteria. I don't think it's a recent discovery, but I just find it really interesting. So next slide. So basically, what is cable bacteria? It's actually just a multicellular microorganism. It's really rare since most microorganisms are not multicellular. They are usually found in soil rich in hydrogen sulfide or poor in oxygen. They are usually in like marine sediments, mud flats, and salt marshes. So what's so special about them is that they can actually conduct electricity through them or current. So this is a very, how to say, big achievement, which I will later talk more about it. But other than that, right, they can also change hydrogen sulfide from deep underground and bind it with the oxygen where there's oxygen place, since they are more attracted to oxygen. It's called chemotaxis, where they respond to higher oxygen level. And they usually just survive based on just electrons. They actually don't need oxygen or that. They just need electrons to live. Next slide. So this is just the structures, and on the top picture is literally the cable bacteria. On the left bottom, actually wait. Okay, I think I'll share screen because I can use pointer.
Okay.
Oh no, I have points here. Never mind. So basically, what's it? Basically, the fibers here are actually stacked cytochromes. It's hypothesized to be stacked cytochrome, as is not yet been, how to say, researched more in depth yet. But they presume it's just stacked cytochromes. So what are cytochromes? It's basically usually just used in electron transport chain. For anyone doing A-level bio, you might know this. It's just basically changing ATP to ATP, generating energy by electron passing through each enzyme. So actually, nanowire is also another form of another bacteria. It's actually discovered quite a long time ago, but only cable bacteria is discovered, I think, this decade, around 5 years ago. So nanowires are basically the genus Shewanella and Geobacter. But for cable bacteria, it's actually not decided yet, but they say it should be a descendant of a delta proteobacteria. They're usually few cm long, it's very long. And then for nanowire is literally nanometers lah. So they conduct electricity or electrons through their pili, but for cable bacteria, it's their fibers. And then wait, there's a lot of discovery for nanowires actually. Since nanowires can be bioremediation of uranium container of petroleum groundwater, since they're high in electron, they can change this into a CO2 byproduct only. They're also already, I think, been used for like oil spillage. They can actually be used to clean up the seawater. There's also theorized to be microbial fuel cell. It's not that efficient, but it can change wastewater into electrical energy. And I think a new study on nanowire is something called Neomorphic Membrane. It's where nanowires conduct a low voltage similar to a neuron in a human brain. So people are trying to make it like for anything that has brain-inspired computing. There's a whole study about it. And then some people also think like maybe they can send this bacteria into space, since they only need to live based on just electrons. So they only need an electron acceptor, which is like maybe iron oxide, which will turn into magnetite, and like that lah. So what's the use for cable bacteria? So people thought of just using it as regulation of Earth soil, since they change iron oxides into magnetite, and iron oxides can bind to like phosphorus containing compounds and hydrogen sulfide. And they also change hydrogen sulfide, making it not toxic to marine life. So we also theorize to be used in biodegradable e-waste, since now making wire, you need a lot of chemical and energy. But for bacteria to grow, also another form of wire, is just sugar. So you can literally grow wire. And it's like here and here, its conductivity can compare with copper. So there's still not much research about it lah, but I think it's quite an interesting topic, and it might rival with like recent technology.
Nice. So just reminder, right? If anyone has any questions, like Abigail, you can just put it in the chat, and each person will get to it later at the end after everyone presents. So if you think of a question while someone else is presenting, you can just type it out, and then we'll get back to it. Okay. So hold that thought, Abigail, and we'll go next. One is Rohan. Do you want to share yours, or I'll share?
You can share it.
Okay.
Oh, okay. So this year, well, I've already pulled up my notes. Wait, hold on.
Sorry?
Give me 1 second.
Yeah.
Okay, so the team of scientists at Rochester University, they found material that is a superconductor at very close to room temperature, 15 degrees Celsius. And this is like a really big improvement compared to like the previous superconductor. It was like this one can be a superconductor at like plus 50 Fahrenheit more. I can go next slide. What? Oh, yeah, okay. So the material requires to be under immense pressure, and like the pressure is equivalent to 3/4 of the pressure at the core of the Earth. It's around 2 million atmospheric pressures. That's a lot. So it's unlikely for it to be used in like bullet trains, like mobile phone towers, because the way they do it is like they take the material and they wedge it between two diamonds, and then like they compress the diamonds really hard, because like the diamonds are able to like withstand the pressure. But like it's still like an improvement. So maybe one day we'll find a material that can be a superconductor at around this temperature or hotter, and then like less pressure. So it's made of next slide. It's made of a mixture of carbon, hydrogen, and sulfur in a microscopic niche. And yeah, like I was saying about the diamond, and like when it's under this immense pressure, it triggers a chemical reaction when they use a laser light. It forms like these crystals, and at around 15 degrees Celsius, the resistance is equal to 0. Yeah, so that's about it.
All right. So just a quick one, right? For those of us who are not super sure, can you just briefly explain what is a superconductor actually?
So a superconductor is a material that can conduct electricity with 0 resistance. So none of the energy is lost while it's transferring electric energy. So like electric heaters, they use materials with high resistance to produce a lot of heat. But if you were to use this material in like the same setup, it would produce no heat, essentially.
And just to add, you see this GIF of this thing going around? That's a superconductor, superconducting metal. And the reason why it's smoking is because they put liquid nitrogen to cool it down. So it's really, really cold. So in real life, most superconductors work at really, really low temperatures, which is why this is a very interesting discovery. Right? Cool. Thanks, Rohan. Next one is Cheryl, I think.
Hi guys. So I think a lot of you know that I'm very interested in renewable energy and like green technology. So today I'll just talk about one type of solar cell, which is actually, I think that it's one of the best solar cells ever like invented. And I think not a lot of people know about this, or like you might come across the word perovskite, but many don't actually know what it means. So next slide. So first I'll talk about the perovskite material. So it's not a material that exists in nature. So it's man-made. Like scientists just take like 3 different materials and like put them together, and it became a material that like can really absorb photon, and so it's a very useful material for the electronics industry. So just to briefly explain, it consists of 3 things, which is an inorganic or organic cation, a positively charged ion, and a metal ion, and a halide ion, which is either chloride, bromide, iodide. And also before I continue, I just want to say that I'll be comparing this perovskite solar cells with other kinds of solar cells, especially silicon solar cell, which is the most common solar cell, the one that is used by KTJ on the rooftops, and also organic solar cell, which is like Oh, can you go back to the previous slide? Which looks something like this also. It's flexible, but instead of using this perovskite material, they only use organic compounds like carbon, hydrogen, oxygen. So yeah, but this perovskite material, besides the organic compound, they add on it with metal and halide, mostly to make it more stable. And like, so basically this perovskite material, you can say that it brings out the best of both silicon and organic solar cells. Next slide. Okay, so I'll just talk a bit about the advantages of this perovskite solar cell. So firstly, as you can see in the picture, it can be printed out very quickly. So that is like it's called a R to R, roll to roll printing station thing. So basically the active material, like the perovskite material, is in a liquid form. So you can just like print it out using a normal inkjet printer on like any substrate. So that's why it's very fast and it doesn't cost a lot of money as compared to silicon, which you have to melt the silicon, purify it, and then make the wafers and then divide the cells and so on. But this one you can just print it on. And secondly, it's defect tolerant, means that okay, so we know that silicon solar cells, they're very hard, they're very sturdy. So yeah, they can last for a long time and that's good. But for organic solar cells, the one that uses like organic compounds like carbon, hydrogen, they can decompose very easily, especially if you put it out in the sun. And then with like rain and heat and everything, they decompose. So with this perovskite solar cell, it's not as sturdy and it is not as long lasting as silicon, but at least it's much better than organic solar cells because with the addition of like the metal and halide compound. And thirdly, it's like it has quite high efficiencies because so for organic solar cells, it the efficiency is not as high because carbon, hydrogen, oxygen, it even though it can absorb photon and convert them to electricity, but it's not as good as silicon. So, and on top of that, for silicon, even though it's such an old technology, so that means for now, if you look at the solar cell like ranking about the efficiency, silicon actually ranks like the highest, like almost one of the highest, but then it sort of hits this like ceiling of like about 40% efficient. So the reason behind that is because silicon, the material is called a indirect band gap material. To make it short, like that kind of material, when sunlight hits it, it requires additional like vibrational energy to convert it to electricity. So that needs more energy. But for perovskite material, it's called a direct band gap material. So when sunlight hits it, it can directly be converted to electricity. So that's why it's higher efficiency. And lastly, it can be made into multi-junction solar cells. So that's very useful because, for example, for a silicon solar cell, like any solar cell, when sunlight hits it, it cannot absorb the full range of that sunlight. It can only absorb part of it. And if you like say attach like two solar cells, one on top of the other, so the one on top can absorb like sunlight from this particular range, and then the one at the bottom can absorb sunlight from the higher range. So that means you can absorb a fuller range of the sun. So yeah, this one because perovskite solar cell is also partly transparent, so it can easily be like put on top of a silicon solar cell just to like easily increase its efficiency by a bit. Next slide. Yeah, as you can see, like the perovskite material, like when the sun shines on it, some light can still pass through, so it's a bit transparent. So now I'll be talking about what are the problems of this solar cell. So first, because perovskite is such a new technology and it's quite challenging to like produce it in large amounts. And And one of the technologies that scientists use to produce it is like CVD, called chemical vapor deposition. So it's like you have to spray, like you cool the perovskite material down to a very you heat the perovskite material up to a very high temperature, and then you spray it on a very cold surface. So it's like a condensation process. So the material condenses on the surface, so you form a very thin layer. So that is quite challenging. And secondly, we have to further increase the lifetime. So even though it lasts longer than organic solar cells, but it doesn't last as long as silicon solar cells. And that's why like silicon solar cells are still one of the are still very much in demand today because of that. And lastly, because remember that perovskite material have to use a metal ion. So most cases, the metal ions used is lead, and lead is toxic also. And it's like in the future, we want to move to like clean energy and renewable energy, and lead is not very renewable, and there's limited amount of lead and it's toxic to the environment. Okay, next slide. Okay, now for interesting stuff about perovskite. So first, Stanford University actually had a research about this, and they discovered a perovskite solar cells called Nobel hot carrier. So what it does is it can reach 66% efficiency, which is more than double of normal silicon cells, which is like that's very interesting because the efficiency ceiling is like, it has been like 30 to 40% for very long, and nobody actually managed to like surpass it. So the reason why this one can achieve more than double the efficiency is because when sunlight hits it, the perovskite material can absorb the photon before the heat gets lost from the photon. So if they minimize that heat loss, then they can really increase the efficiency a lot. And the next one, which is quite interesting also, is in order to make it more stable, to make the perovskite material more stable and more resilient, they utilize like the design of a compound eye of the insect. So like this fly, the eye of a fly with like hexagonal like shapes like that. So on top of the fly is like an example of like the perovskite material that they make based on the compound eyes of the insect. So by doing this, they are able to make it stronger and like can tolerate heat and humidity a lot better. Yeah, that's all from me. Thank you.
Nice one. Okay, since we have a bit of time to spare, just a quick one, Cheryl. I think Abigail wants to know, what's the difference between solar cell and solar panel?
Okay, so a solar cell is like just one. So a solar panel is made up of a lot of solar cells. So yeah, the one on KTJ is like that big thing is a solar panel, and you might not be able to see it closely, but it consists of individual like blue square brackets, which is the individual solar cell. Yeah.
Why would we need to like have solar panels, like a solar cell free? I mean, why were solar panels invented first then? Like if we could have just used like solar cells.
Because solar cells because solar cell is just it's just one single thing. So you have to connect a few solar cell in order to produce enough electricity to power something. So one solar cell cannot generate as much electricity by itself. So you have to connect it like either in series or connect it in series to plus together all the current generated.
So like this one, like this solar cell is like, it's just one solar cell, but it can produce.
Oh, can you go back to like the previous slide? No, wait, which slide was it? Back to, yeah, the printing one. Yeah, okay, so for this solar cell, right, because it's different from the solar cell on top of KTJ, the one on top of KTJ, you can imagine those solar cells like bricks, like they're individual components, like individual like rectangular blocks. But this one, because it's in a liquid form, you don't have to like make the individual blocks. You can just print it out like in one line, and then if you want to separate this material into like individual cells, you can just scrape it. So like you see this long line of orange thing here, so you can just like stop spraying any material, and then there will be nothing here, and then you continue spraying material. So you don't have to make like individual blocks. Okay.
Yeah. Okay. Thank you for the clarification. Yeah.
So I think it's my turn now. And since Cheryl was talking about how we turn light into energy, I'm going to talk about the exact opposite of light, which is dark. So I'm going to talk about black holes. And this has been a personal favorite of mine for a long time. So the fact that last year we had like such a big discovery in black holes, and this year we had a Nobel Prize in black holes makes me really excited. So just before we start, I'm pretty sure everyone knows generally what a black hole is. Is there anyone who doesn't know what a black hole is so far? I'll assume that you guys know what a black hole is. I'm not going to explain too much what a black hole is. But the thing about black holes is that they were theoretical for a long time. Einstein's equations predicted them in the 60s. And there were, later I'll show you who actually did the calculation to prove black holes. And for a long time, they were just theoretical. We had no evidence that they existed in real life until last year. So for a long time, they've been doing all these measurements to see whether there was really something in the center of every galaxy, which is something very dark, but it has a lot of mass. And last year, we finally got to take a picture of it. This big thing here, this GIF, this is not the picture. This is the picture at the side here. So the picture is very blurry because it's very, very far away, even though it's super massive. And what you can see is that there's a ring of light surrounding this very dark object. And this is supported by data seeing stars orbiting that object as well. So we know that there must be something really dark in the center, surrounded by really bright things. And the reason why it's really bright around it is because of this disk. So this illustration is what NASA thinks that it might actually look like. So what this disk is, it's super hot gases that is surrounding the black hole. And since they're moving so fast, they collide with each other at high speeds, they cause so much friction that they start to heat up and glow. So if you guys watch the film Interstellar, then this would be very familiar to you because this is the exact simulation that they used for the black hole in the movie. In fact, that's the first movie to use an accurate simulation of a black hole. So that's very interesting. But I'm going to talk to you about the Nobel Prize in Physics 2020. So these are the winners of the Nobel Prize 2020 in physics. And it's 3 people, which is the maximum limit for Nobel Prize winners per year, per field. And the first one I'm going to talk about is Sir Roger Penrose. So if you followed physics for a long time, this guy, his name comes everywhere. He's in charge of everything. He's a mathematician, he's a physician. If you are into art, you can search his name up for Penrose diagrams because he invented some of those illustrations where you have something that tiles infinitely. So if you've seen a carpet with all those patterns, he's the one who invented it. Anyway, he's also contributed to black holes. So since 1965, he's been using Einstein's equations to try to prove that black holes exist. And he did that even though Einstein himself believed that black holes didn't exist. Einstein didn't believe in his own theories. He thought that he was wrong. But after he died, with the help of Stephen Hawking, Roger Penrose decided to use his equations to prove that black holes exist. So because of those efforts, ever since 1965 up until last year, he finally got Nobel Prize this year. Okay, but all these theoretical stuff, science isn't just about theory. Science is about proof. You need to be able to come up with a theory and show that it actually exists in the real world. And that's where these two come in. This is Professor Andrea Ghez, and this is Professor Reinhard Genzel. And these two have been working as separate teams, one in Hawaii and one in Chile, to actually discover, to actually look at proof that there's a real black hole in the center of our galaxy. So Professor Andrea has been studying at UCLA and she's been working in Hawaii for 25 years, and so has Professor Genzel. And I'm going to show you what they found. So this is their actual data. So all the simulations you see of black holes, they look really cool. There's a black thing, there's light coming out everywhere, but this is what the scientists actually see. So they're mapping out over 20 years the movements of the stars near this object. So this white color object is the black hole, and each color around it is a different star. And as you can see, between 1995 and 2011, a lot of these stars are moving really, really fast. It only takes 16 years for this star, this closest one, this one. You see the pink color one is moving really fast, and the yellow one is moving really fast. It takes it 16 years to travel that distance, which is equivalent to 3 solar systems worth of distance. And it's a really fast star. And the only thing that can make it move that fast in orbit is something with really, really high mass in the center. So what they did is, using the equations of gravitation, they can calculate based on the period of this star using Kepler's laws to find the mass of the black hole in the center. And it's really big. The results were, it was 2.5 million times the mass of the sun. So that's the black hole that discovered in the center of our galaxy, and it's called Sagittarius Sagittarius A star. So there's a few challenges when they had to do this. The first things was, all these telescopes that they worked at was on Earth. It wasn't in space. And on Earth, if you look up into the sky at night, even if it's a clear day, you still have atmospheric interference. And this is a big problem when you're trying to track really accurate movements of stars over many, many years. So they had to come up with a few solutions. The main one, which is what they actually won the Nobel Prize for, was the invention of adaptive optics. So how regular telescopes work is that you have a mirror, and then you have a lens, and then the mirror reflects light into the lens, and the lens focuses that light onto an imaging device. Usually it's a sensor or something. But if there's tiny movements in the lens or tiny movements in the mirror, the reflection changes, the angle changes. So this is a problem if you don't want the changes. But what if the atmosphere has interference and the light is refracting randomly, and you want to change your mirror to be able to counteract those changes in the atmosphere? So what they have is they have an AI that measures the changes in the light above, and then they oppose those changes using the mirror. And that's called adaptive optics. It's basically a telescope that can change based on what's happening around you. So this is what Professor Andrea won her prize for, because she's been pioneering this for over 20 years. And the second thing that they did was they combined data from a bunch of different observatories. Because if you have a lot of data, you can average it out to find the real correct data, which is why you need to have 2 teams to discover this instead of just one. So this is how they overcame the challenge. And for those of you wondering, if you followed the news last year, this was a separate black hole. The picture that they took last year was not of the black hole that Professor Andrea and Professor Reinhardt were studying. This is a different one. The one that they were studying, these people, are the one in the center, is the one in the center of our galaxy, the Milky Way. But this one that they took a picture of last year is the black hole in the center of another galaxy, M87, which is millions of light years away from us. So they're studying 2 different things, but they both came to the same conclusions, is that black holes exist. And there's one thing that a lot of people were questioning is, why didn't the people who took picture of the black hole win the Nobel Prize? And it's because this was a quite new discovery and they haven't been working on it for a long time. They might win a Nobel Prize in the future because you need to confirm your data in the future first. Just because you get data doesn't mean it's correct. So we need to be able to follow up science with more science in the coming years. And that's about it. That's my presentation. I do have a video, but I'm not sure if we have time to get to it. If you want to do discussions first. Yes, this is the perfect time to buy Bitcoin. Sorry, my roommate. All right, so do you guys want to start asking questions based on each presentation?
I have a question.
Yeah.
For the black hole. I mean, like, I was.
Wait. Abigail, before that, I think you should just type it into the chat, and I think we should follow everyone's presentations.
Oh, okay.
Yeah. Sorry.
By the way, I just finalized.
Okay, so who was the first one just now? Sean. Anyone have any questions for Sean? Zilong, what was that you shared?
It's how nanowires can, how to say, used in neurologists.
Sorry.
No, he just shared something for you to check out later.
It's a neomorphic membrane.
I have one quick question about the paint thing, right? The chili thing, right? So so actually our sensation of temperature isn't based on actual temperature, right? You said it's based on changes in temperature.
Yeah.
Do you know why chili causes that?
As far as I know, is because of the ions and ion channels, and then there's ions actively transport around the membrane, which then cause impulses to send it to our brain, CNS, central nervous system, and then it then relay. Yeah, so that's what happens, I think.
And I guess if
I'm
you
sorry.
oh yeah, sure.
Sorry, I don't understand.
But sorry,
I didn't get that. I don't understand. Yeah.
you don't understand what I say?
Yeah.
Okay, so in order for us to have impulses, we need to activate basically we have to have electrical impulses to start off, right? So what our body do to achieve that is that we have something called resting potential, and then that is that the difference between the membrane inside the axon, which are neuron. So inside the axon and outside the axon, there's different charges. So then the difference is called the resting potential. So when the potential changes, right, it then causes a chain reaction on its neighbor. I'll just say that is easier to understand. So then the neighbor will get it and get it and get it and get it. So then eventually it will pass it on one way, one direction to our central nervous system. And then from there, our brain will take it and and then the brain will know what is going on, and then they'll send back impulses to our effectors.
So
You understand?
Oh, okay. Yeah.
just
Yeah, I understand
to
now.
simplify things, right? I just want to make sure I'm correct because I'm not the biologist. I don't know anything about biology. But if you say it like that, right, then our brains are all just circuits, right?
Yeah, but we
And
have chemical terminals.
yeah. So this is I tried to draw a synapse, and what you have is just a different charge on one side and different charge on the other side. And if you want to fire it, you just need to connect them, and then the charge can flow, right?
Not
really.
Neurotransmitters, right?
Neurotransmitters can flow.
Yeah, I don't think it connects, but
Yeah, they don't touch.
it is actually it causes the membrane to be permeable, and then so then the calcium ions will diffuse into the presynaptic one.
Yeah.
And then
So,
after
soft
that, the neurotransmitter will and then will go across into the plus. Let's say the minus is the presynaptic, and then the neurotransmitter will release and go into the plus one where you draw one. And after it attach there and changes the receptor shapes, it then activate on that postsynaptic what we call postsynaptic membrane. And then so it's basically not connected. It's actually break off, and then it's the neurotransmitter to pass it on the signals, and then they take the signal and then they activate again the signals. So then they will make sure that it's one way direction, and and it's like they have to get rid of useless information. It's also one way. Okay.
So
If you
the
take
thing,
if you take A-level bio, there's a whole topic about this.
Yeah, there's a whole chapter about it. I mean,
my god.
IG and STM bio also. But one thing that I find interesting, right, is that in all our circuits, everything, we use electrons as our charge carriers to carry charge. Electrons, right? E minus, E minus. But in all the biological stuff, in cells, in humans, it's all ions. Ca plus, K plus, everything.
Yeah, it's actually how interesting that they make it negative by not by gaining electrons, but they throw out the protons.
Yeah, very interesting.
That's
Okay. That relates very nicely to Zilong's one because he's also talking about like ion transfer.
Mine is more like instead of using synapse, we do more in E&E. That's what I sent to Sean lah. Like since we can't really do much, I don't understand the brain much yet. But people are thinking of using nanowires to implement with the brain since their voltage are almost the same.
So we can just like build wires into your brain.
Yeah, so it's like a separate memory in your brain.
Or like you can store like a SD card in your brain.
Yeah.
Yeah, basically
that.
what's Neuralink trying to do. Elon Musk.
Elon Musk. Every session in STEM, we always end up talking about Elon Musk. For
Yes.
some reason.
Legend.
Legend.
He's a god.
Yeah. And
we can also like forget stuff, like if we have this memory thing which we don't want to remember, like some really bad traumatic events, can we forget that?
Yes, actually.
yeah, just by deleting it.
That'd be cool.
But that's actually scary because what people can do is that you can force someone to just delete something, forget something. You can forget someone ever existed just by deleting their part.
But what
Really scary.
neuroscientists believe is that to learn is to actually unlearn. So you have to unlearn something, then you have to learn. Yeah. That's what they say, I think.
And then Abigail, you wanted to ask about Zilong's one, like multicellular. What was that?
Yeah, it's like so like these cable bacteria, right?
Yeah.
So like I forgot what they do again. They do stuff like with the hydrogen and oxygen, and
they perform redox reaction basically. So they just transport electrons from one place to another.
So like okay. So are they able to do this because they are multicellular? Like
they are able to do this because they technically multicellular, just so they can be long, but they also have the stacked cytochromes.
So they can do it. Zilong.
Yeah.
They can do it themselves, right? You just have one. They can do it themselves, right?
Yeah. So that's just nanowire lah. That's just nanowire.
But then if you connect a lot of them together,
then it becomes a cable lah, a wire. Nanowires are basically just. Oh, sorry.
Wait, so like you connect many. I'm actually a bit confused with the stuff covered today. So if you can connect like many nanowires to form like a cable bacteria, I'm actually confused with what's up.
Technically, almost the same, but how do that? I think I'll draw better.
Yeah, you should draw. You can draw mine.
No. Oh yeah, wait. Annotate. So nanowires are basically just one organism, and then they have pili, which is like just say a sea urchin. It's like a sea urchin, and then they can carry just change color. Tiny electrons on their pili. So they just stuck it to them, and then they'll carry this off to maybe iron oxide lah, which then they can change to magnetite lah. So
what's magnet?
It's just like Fe something, I forgot already.
Magnetite is it's a compound of iron. It's the magnetic thing in magnets.
Oh, okay.
So for cable bacteria, they are basically just one long strand, like just multiple bacteria together like that.
Oh, okay.
They actually don't have this pili. They have this one long fiber outside, which then can conduct electron, and then it goes from the electrons doesn't stay. It literally just goes in, goes straight up, out, like a wire lah. So instead of like a normal nanowire, it holds the electron until it finds an electron acceptor. This one just transmit it instantly. So usually in seawater, deep underground, there's no oxygen. They need oxygen for being an electron acceptor. So the top part acts like a snorkel lah. So here is usually just oxygen, O2, accepting it, and here are the hydrogen sulfide. They are their food source.
Are these things? Sorry. There's something, Abigail?
Oh, nothing.
Zilong, are these things like naturally occurring? Like they're just hanging out in real life? Yeah, right.
Yeah, they're actually quite common.
Yeah, so because you said scientists discovered this thing, how do you I'm not very sure
How do they
discover.
discover? Is it?
Like, did they just run a current through it and be like, oh, this thing is conductive?
It first discovered by they just take a beaker, they put mud in it, they put mud in it, and then they take out all those types that can maybe like how to say those worms that can go in, and then oxygen can diffuse, which then the H2S can also diffuse out like that. So they basically found out that this is actually how to say changing much faster when it goes out. So they're not smelling the foul smell of this lah. So they realized they thought of like a lot of things, but then their conclusion is there was another bacteria putting the oxygen into here or just transmitting the electron out.
That's very clever.
So they found this bacteria, which actually is a lot of this bacteria. You can actually see it with your naked eye. If
It's
there's
big,
a
right?
lot
It's
of
like
it.
centimeters long, right?
Yeah.
That's scary. I don't want to like touch a bacteria.
I mean, they're not harmful lah. They're
Yeah,
just,
but it's gross lah.
I think the way they found it to be conductive was they put it like on an electrode, since they just conduct. So they actually grow them on electrodes because they don't need much to live. So if they just have electrons, they can actually grow forever. And I think this can be called a biofilm.
Yeah, this is what they use for biofilm.
I don't know about that. They actually glow. If you actually conduct, they actually glow.
Oh, that's cool. That's cool. Okay, we're running out of time soon, so I think we're just gonna quickly run through any last questions that we have. For Cheryl's one, I mean, I feel like Cheryl already explained why we don't use the solar cells because it's new, and also the drawbacks, right?
Yeah, one thing, Cheryl, I got one question for you. Do you think in future we can put solar panels on car, like Tesla, right? We can just put solar panels on it. We don't have to charge, and then we can just keep using it because you got sunlight. And then at night you can just use the store. Yeah. Do you think it happens?
Actually, like right now, there's quite a few like solar car competitions where they build cars that's only run on solar panels, but those cars are like they have to make it very, very lightweight, very, very aerodynamic, because the current that you can, like for now, the current that can be absorbed by the amount of solar cells you can actually put on a car is not enough to power a full-size car. So yeah, that boils down to the efficiency for now lah, because like for example, one solar panel, like this area of solar panel, it can only be like 30-40% efficient. Then yeah, you can only power like super small one-man car, and it has to be very well designed so that it's aerodynamic. So you need minimal air drag, minimal resistance and everything. Yeah, until they can up the efficiency. Not for a normal car.
Okay. Can I ask one more question? Fine, can I? Is that
Go ahead.
Okay. So, since now we're having too much CO2, right? That's why we trying to use renewable, right? What do you think will be the problem if everyone uses solar panels? Like, okay, for example, too much demand for metal, something like that. What do you think?
Yeah. So basically now, because silicon is okay, silicon is basically from sand. Like we have a lot of sand, but so if we were to depend on silicon, we won't be able to produce them fast enough because it takes very long and very high temperature and everything to process. So if we depend on silicon alone, it won't be able to satisfy the whole community. So that's why they're like trying to research about different types of alternatives. So the other types, a lot of the other types actually, they use a lot of the metals like cadmium, like even though very high efficiency, but not enough for the whole world, like very, very little left in the world. So that's why I think like organic solar cells are one of the best option already, because it's quick, like you can get carbon, hydrogen, oxygen from anywhere. But the drawback of that is it's not stable. It's not very stable. It decomposes very fast, especially you put it out in the sun. So And then the next alternative is perovskite law. So it uses mostly renewables, like mostly materials that are very easy to find, except there's this like tiny metal component which they're trying to like see whether there's any way through it.
And I guess for me, what's your questions? What does the star move? Does the sun move? The sun move because of black hole, but really slowly because the black hole is not so strong. Okay, I'm just gonna draw it out again. Okay, Cheryl, what do you mean? Like, why does the star move? Is that it? Why does it move?
The sun doesn't move, right? So why does the
So here's the
sun move?
It very slowly, right? Like it orbits around the Milky Way, does it?
yeah.
But very
So
slowly.
actually, here's the thing: the sun does move, and it's moving really, really, really fast. Actually, but the
Okay.
thing is, so if I'm just gonna draw, this is the sun, and this is the Earth, blue, and it moves. Do you notice the Earth move? Not really. You don't feel it move, and the reason why we don't feel it move because we're also moving with it. But you can extend this logic to say that the sun is also moving across something else. So let's say there's another massive object really far away, and the sun is moving around it really, really fast. And you can ask, okay, why does the sun move around this thing? It's the same reason why does the Earth move around the sun? It's because the Earth is already moving in space. If there was no sun, let's say I have an object. Let's say I just have this baseball or something, it's just moving throughout space. It's going to move in a straight line because inertia says that it won't stop unless there's any force, right? But if I have a mass near it, then it will start to accelerate towards the mass. And if the mass is just right, it will start to orbit the mass. It will continue to move sideways because of inertia, but it will also have a centripetal acceleration towards the mass because the mass attracts it. So it's going to orbit. So the reason why the stars move is because the stars have mass, and there's something in the center of the galaxy that's holding all of the stars in this orbit. All of the stars are orbiting the galaxy in this rotation. There's another star here, all orbiting there. So that's what they discovered. We know that there's a lot of stars in the Milky Way, and we know that all of them are moving because over the years we can see how the stars move. The constellations change slightly over the years, and we know that they're moving across this thing in the center. So how did the fast-moving stars in the center show that there's a black hole? It's because of Kepler's law. Kepler's law says that the closer you are to the center of your orbit, the faster you have to go to keep up the orbit. So if you look at the solar system, you can see that closer to the sun, you actually have to move a lot faster to keep up. Mercury moves really, really fast. Venus moves a bit slower. Earth moves even slower, and etc., etc. If you go out, the slower you start to rotate. So if you follow this logic, the closer you are to this thing, you have to move really, really fast to keep your orbit. If not, if you slow down just a bit, you fall into the thing. So that's what was happening in the center of our galaxy. In the center of our galaxy, there's something with so much mass that to stay in orbit around it, the stars around it have to move really fast. And you have to keep in mind that by really fast, I mean they travel around the thing in 16 years. Because the distance, 16 years is really fast because the distance between here and here is like 3 times the solar system. A really long time over a really, really long distance means a really, really short, really, really large speed. It's moving very fast. So that's how they figured out there's a black hole in there. And for Harun,
do we know what that thing is though?
it's a black hole. Yeah, so all we are moving around a black hole. And
so it's like we need black holes for like space to exist, or and like to be honest, like we need black holes for life to exist.
Basically,
like, without
Earth,
without Earth, we don't have, without the sun we don't have Earth, and without the sun we don't have black holes.
Yeah, definitely. That's a good point because black holes are formed from dead stars, and if there were no stars, there would be no black holes, and everything nicely fits together, lah. Because without this black hole, we wouldn't have the galaxy. The galaxy would just be scattered. The reason why we circle around this thing is because it has a lot of mass in the center. Okay, just for a quick one for Harun's question, the reason why we didn't photograph this one is because there's a lot of interference. We are in the Milky Way. We are in the Milky Way. The black hole is in the center, but we are here. And if you want to point our telescopes at the thing, we have to pass through a lot of stars. There's a lot of stars there. But the galaxy that we took a picture of was perpendicular to us. So number one, okay, it's very far away, it's larger distance, but there's less stars in between. So there's less interference due to gravitational lensing and other stuff. So we actually get a clearer picture of this black hole than this one, even though this one is further away. It's all about perspective, which is why, like, you can, if you look up, you can see up clearer, the sky clearer than if you look very far away to mountains. The mountains in the further away look very hazy because of interference. Same thing happens here.
Right.
Okay, I think that's pretty much it, right? Yeah, so that's our last session for this year. Clap, clap. STEM Clap 2020.
This term.
I mean, 2020. So next year, I don't think we have time for discussions now, but we can have discussions in the classroom and in the chat, and maybe we'll come up with more activities. I'm going to send out something to the Google Classroom later, and it's basically this doc full of ideas. If anyone here has any ideas they want to contribute, any sessions that you want to hold, or if you want someone else to hold, you can also suggest. It's just a Google Doc where you just put in ideas. So next year we'll see which ones we can get to. We'll try to do as much as we can. Cool?
Do we have to?
Yeah. Sorry?
Like say that I want this person. Can we just like say the topic?
Yeah, sure. And as vague or as detailed as you want. I'll send a doc later. You can take a look later. Okay? All right. Thanks, everyone. See you guys next year.
Guys. Bye.
Thank you.
See you. Thank you.
Mr. Allen? Sir?
Hi, FM.
Yep. I just reminded that Mirza and Shay are not here, so thank God we recorded. You can post it to the classroom and they can see.
Yeah, of course. Yeah, not a problem.
All right.
Thank you very much for organizing that. Really interesting topics.
Yep. Guess that's it for this year.